Thank you, Chairperson. I am Mutsumi Kimura from Ryukoku University and NAIST. And I think that Ryukoku University is not so famous in this area except for the Kansai area. So that please memorize this one thing. Ryukoku University is the eldest university in Japan because the Ryukoku University is established by the idea of Shinran, Jodo Shinshu leader. So that more than 780 history Ryukoku University has. And in my case, I belong to not only the Ryukoku University and the NAIST. Material and device jobs are done in the Ryukoku University, and the computing and architecture works done in NAIST. As a result, we have a very good result on the brain type integrated system using thin film devices. As you know, there are many good results showing the performance of the artificial intelligence AI. The AI defeated Ego champion 2 years ago, and now AI can write a novel. And you can use a very high performance AI from the IBM only if you pay the very expensive money. Okay, so recently the shogi champion was lost by the AI program. So I think in the next April, it will be announced that the age will be age of the Jinko Chino. Okay, this is a laughing point, please. But still, there are several problems. The current AI is software executed on the hardware, very, very long and complicated software, and the hardware should be a high-performance Neumann type computer. As a result, the size of this server, AI server, is very bulky, and this server consumes a very, very high power, not only for operation of the computer, but also the cooling machine, air conditioner. Huge power must be consumed. So and one of the keyword current society is IoT, Internet of Things. And recently, T is changed to the E, Internet of Everything. And I would like to add A, AI of everything, which means that everything, the AI can be installed on the everything. You know, the Society 5.0 is a very interesting, focusing keyword, and in the Society 5.0, edge computing is very important. Edge computing means that some very high performance computing is done in the each items. So that in order to realize the edge computing, of course, it is impossible to use a bulky and a low speed, high performance, fragile computer. Instead of by replacing this computer, some kind of AI autonomous system is very available. In this system, this system should be very compact, super low power consumption, and robust. Robust means that, for example, in your brain, every day, 100,000 neurons is dying every day in your brain. But you can lie. This is because the brain type computing system is very robust. You have. Okay, so I think that I have an idea to make a neuromorphic brain type hardware computing system is very suitable for the AI technology. And this is the history of the computer and the current AI. It is very famous that in 1947, in the Christmas Eve, the transistor was invented. And in order to use the transistor, CMOS technology and the digital technology and high integration, etc., was developed. So that finally the very high performance computer was developed. But the computer architecture, conventional computer architecture is completely different from the artificial intelligence architecture. So that many and very large software is necessary to connect the gap between the architecture of the computer and artificial intelligence. And some researchers have already found it, noticed it, and they would like to make a neuromorphic system to realize the artificial intelligence. Neuromorphic system is defined as a brain-type computer. The neuromorphic system has a very similar architecture of the human brain. But there are many approaches. First one is by using CMOS transistor and the neuromorphic system is developed, and by using a Neumann type computer, neuromorphic system is developed. But our approach is completely different. In order to make a neuromorphic system, all the devices, all the structures should be revised. For example, what material is suitable for the neuromorphic system, what device structure, what algorithm is suitable for the neuromorphic system. The most important things in order to realize this, these items should be simple and large scale integration is possible and real-time computing is also possible, and in order to make a very low-cost device, these fabrication process and the materials are very productive. As a result, if we can make a neuromorphic type, real neuromorphic system we can get, which will be a compact, low power consumption, and robust. And each item we propose first for the material, amorphous metal oxide semiconductor. This is very promising semiconductor devices, materials, and as for the devices in film, the variable resistance and the variable capacitance structure should be the three-dimensional integration is necessary, and algorithm is also important. Some kind of local automatic learning algorithm is necessary. I will explain each item one by one from now. This is the current technology of the neuromorphic computer, and I think the IBM True North is most famous neuromorphic computer. I had 2014 this was published. This is a very good CPU, but neuron 1 mega, synapse 256 mega, etc. But by using this IBM True North, if we would like to make a large scale comparable to the human brain, the power consumption should be the 6 kilowatt. On the other hand, the human brain consumes energy 20 watt. Still there are large gap. This is because this kind of neuromorphic system is not a true neuromorphic system, because some kind of silicon technologies are used. So that I would like to replace all the technology to the other technology which is suitable for the neuromorphic system. First, material, I said the amorphous metal oxide semiconductor I would like to use. One of the widely used application of the amorphous metal oxide semiconductor is IGZO. Maybe some of you already heard this word, IGZO, indium gallium zinc oxide. This is very famous material for the flat panel display, liquid crystal display, and active material, organic light emitting display, etc. But I think that this material is not only for the FPD, but also for the other applications. There are some very good features for in the amorphous oxide metal semiconductor. For example, the metal oxide, several metal and several oxide. So the several metal and oxide semiconductor, so the very complicated compound material, which means the various characteristics can be realized using the control of the composition of the atomic elements. And oxide means very stable. Usually silicon is degraded by the inclusion of the oxide, but this material originally includes the oxide, so that even if oxygen is included, no degradation, very stable in the air. So that as a result, room temperature fabrication and the printer process is possible. And this device is amorphous, which means that no high temperature is necessary to crystallize the material. As a result, this device can give various interesting performance, and fabricated on the large area, and the three-dimensional structure is also possible. Also, there are some disadvantages. Performance is not so high in comparison with the silicon transistor, and yield not is so high. But if this is an example of the three-dimensional structure semiconductor technology. You know the AMOLED. AMOLED is, for example, the iPhone 10, the front display is AMOLED. On the transistor, some kind of OLED light emitting device is stacked. This is the stacked structure of the semiconductor. I think this is the first product of the stacked structure three-dimensional devices. You know that some people say that using the silicon technology, three-dimensional structure is obtained. But in that case, the wafer level bonding. In this case, the film level integration. I think this is very interesting technology, and this is our previous presentation. On the organic transistor, we deposited oxide transistor, so the very challenging, but we confirmed that the performance of these devices. And if these advantages can be effective, and these disadvantages is acceptable, the novel application can be made. One of such a novel application is a neuromorphic system. In other words, in order to make a neuromorphic system, this material will be very suitable And as for devices, I think that some kind of thin film variable resistance is very good, suitable for this application. The first one is this one. Just a thin film conductor, IGZO film here. IGZO film is transparent, so that you cannot see the IGZO film, but there is a IGZO film here, and this is electrode. This is just a conductor, and by applying a voltage, electric current flows, of course. And then this is relationship between the bias time and the electric current. As you can see this figure, the electric current gradually decreasing. And this is because this is a substrate and a glass substrate, and this is a semiconductor here. And by flowing the current, electrons collide with the film atom, and there is some traps are generated here, and these traps capture the electron, and free carrier decreasing, and the conductance is decreasing. And but anyway, it is important. Along the time, electric current is decreasing. This characteristic will be utilized for the learning rule of the neuromorphic system. And this is another type of the amorphous oxide semiconductor. This is a cross-point type. There are many cross-points here. There are actually the 6,400 cross-points are here. And each cross-point, this is a structure that by applying the voltage, current, electric current flows in the vertical direction. And this is also the relationship between the bias time and electric current. You can see that electric current is decreasing around the time. And as I said, the algorithm is also important. Local automatic learning is very, very suitable for the neuromorphic system. In the current AI, some learning is done in the simulator, and the data is downloaded to the actual devices. In order to do that, very high performance server is necessary for the learning. But in your brain, there is no server here. So that in the human brain, the learning is done itself inside. So that some kind of automatic and local learning is necessary. Hebbian learning, this is very historical and famous learning process that is very is shown here. That this is the one synapse and one neuron, and this is the other neuron. This is the synapse. If the two neurons are in the firing state, the synapse strength is enhanced. This is a historical Hebbian learning. But this learning rule is a little difficult to apply the electric devices. So that we changed a little to the modified Hebbian learning. In this learning, the one neuron is firing state and the other neuron is stable state. The synaptic weight is regulated. This is vice versa. So that I think that it is necessary to confirm that this learning rule can be used for the used as a learning rule for the neuromorphic system. From now, I will show you the example of our proposal. Actual experimental result. This is the result of the Hopfield neural network and the amorphous deep Gaussian film devices as the synapses. And this is the actual photograph, and there is a cross-point type device. Amorphous oxide semiconductor synapses are 6,400 synapses are located here. This is the circuit diagram. This cross point is here, and this circuit is composed in this circuit board. This is a conventional type of the Hopfield neural network. So this neural network structure is not so new, but the novel point is this amorphous oxide semiconductor is integrated in this system. And here we taught some kind of character. Here we taught two characters, T and L, and several times, several minutes, and several hours. And after the learning process, this neuromorphic system can return a correct T and L, even if some distorted pattern is inputted, which means that this neuromorphic system can reproduce the pattern later learned by the previously. Okay, so that this is a kind of later reproduction, or some people said that this is associated memory. That some kind of learned pattern is outputted, even if a little different pattern is inputted. And this cross-point device is the only single layer. But now we succeeded in developing a two-layer stacked layer. And this is the result of the learning process. The 0 and 1 pattern is learned, and a little different, a little distorted pattern is inputted, but this system returns the correct system, correct patterns. This is also the success of the pattern reproduction. And this is second, two layers, but in principle, more and more layer stack is possible. So that in the future, I think the 100 and 1,000 layered structure, which will be an actual three-dimensional structure for the neuromorphic system. And this is the other example. In this example, on the LSI, this LSI has many neurons. This is the neuron pattern, only two inverters. And at the top layer of the neuron, we deposited amorphous IGZO semiconductor here. So that LSI has a function of the neuron, and amorphous IGZO film has a function of the synapses. Also, in this pattern, on this device, on this system, we taught a T and L. And even if a little distorted pattern is inputted to this device for a while, this device returns the correct pattern T and L. Again, we succeeded in making a later recognition system using a neuromorphic system. And this is brand new result. As I said, we use the degradation of the amorphous oxide semiconductor, so that if the degradation is completely degraded, no more memorize is possible. So that now we would like to change the amorphous oxide semiconductor to the memory star device. Memory star device is one of the famous devices for the novel future memory, digital memory device. But we would like to use this one for the neuromorphic devices. There is no time to explain, so please read the. I think that in a few weeks, this result will be published in the scientific report, so please read it. And the other possibilities of ferroelectric capacitance devices. And one problem to use the resistance type device is power consumption. Resistance device consumes power, DC power. So that I would like to replace that by the ferroelectric capacitance. Ferroelectric capacitance means that capacitance can be changed by the applied voltage, so that this capacitance change can be used as a synaptic weight. Okay, this is the result of the this device characteristic, and we made this device and integrated in the Hopfield type neuromorphic system. And sorry, it is Japanese, but we have already confirmed that this device also can run a T and L and succeeded in the reproduction of the T and L. Okay, finally, I would like to conclude my talk. As I said, current AI system consumes a very high power, so that in order to widely use the AI system, some kind of hardware system is very desirable. So that I think the combination of the software and the hardware AI, hybrid AI system will be available in the future. The advantage of this system is a very compact, super low high power consumption, and robust. Even if the internet is not connected, this device can work with the hardware type AI system. Okay, I would like to thank the if you would like to study more for the artificial intelligence, I have already published this one, so that please buy it. If you buy one, I can get 100 yen. Okay, thank you.